Our CS51 project group set out to create a virtual chess simulator, and our group consisted of Michael Gribbin, Michael Huntley, David Campos, and Max Scherer. In terms of an overview for the project, we sought out to create a user-playable virtual chess simulator that follows all of the classical rules of the game. The algorithm that we implemented is a Nigamax algorithm that uses a technique called alpha-beta pruning, which is built off of the Minimax algorithm. We implemented optimizations and heuristics to try to improve runtime efficiency as the project progressed. Furthermore, we made it such that algorithms can compete once against one another or against the player to examine the different performances of the various algorithms. As far as motivation for the project, all of us shared an interest in chess as a strategically interesting and dynamic game. The classic problem in computing is to design a chess algorithm that's essentially unbeatable, and as of yet it's been unsolved. While we didn't strive to create an unbeatable chess algorithm, this was certainly an interesting problem that we thought it would be a good experience to gain some insight into. There's also a great deal of room for customization and personal input, which always makes for an interesting challenge. As far as the algorithms and data structures we used, we began with the random algorithm to promote the effective UI testing while we were trying to design the user interface at the beginning of the project. We then moved on to design a Minimax algorithm as an introduction to intelligent computer play, and built off of this a Nigamax algorithm, which essentially increases the speed and improves upon the organizational clarity of a Minimax algorithm. Finally, we implemented alpha-beta pruning and explored a couple of heuristics for runtime optimization, ultimately settling upon a null move heuristic as a very efficient improvement. Finally, in terms of the data structure, we used an array representation of the chessboard as we felt it was the most intuitive way of doing it with which we were most familiar. So here you'll see, sped up substantially, a player on the white side playing against the Minimax algorithm on the black side. The Minimax algorithm attempts to value a board at each possible stage based upon a depth that looks a certain number of turns into the future. In this simulation, the Minimax algorithm is employing a depth of 2 to look at the valuation of the board after the player goes and then after it goes the following turn. The way that the board is valued assigns a certain weight to each piece, which placing importance of differing levels on different pieces. Furthermore, it assigns a mobility value to all the possible pieces on its board, and assigns a weight to that mobility value, with the idea that a more open board is a better board in terms of adaptability and the capacity of the algorithm to move around. While the algorithm certainly isn't perfectly intelligent, we did notice that as compared to something like a random algorithm, it consistently destroys the random algorithm in play, and is certainly a good bit more intelligent than that. All in all, we really enjoyed the project and thought it was very algorithmically stimulating. It took us quite a while to design our UI, which was one of the big challenges of the project, but we felt it was a pretty rewarding experience overall. Thanks for listening.